Okay, so we've pretty much figured out our pin out, so let's start having a poke around, see if we can figure out the details of how this thing works. Right, when I was poking around, I just noticed a set of 3 really small pads right at the edge of the board, so I'm thinking, well, that's probably a COM port, so stuck a scope probe on it, found some 115k UART traffic, so let's have a quick look at that. Right, this is what we get when we power up. And the biggest surprise is this thing's running Linux. Now, I was a little bit curious as to why they had such a big RAM and flash chip in there, so that certainly explains that. Also explains why it takes about 5 seconds to start up when you sort of plug it in. But it seems a bit of overkill to run Linux, so this is basically just sort of squirting data around and not really doing much else. It just seems a little bit of overkill to have an old operating system in there. There isn't anything particularly interesting in here. I don't think there's really anything particularly interesting in here. Some stuff about booting from flash. It gives a login prompt. I tried a few obvious logins, but I couldn't get in. I can't really think what you could usefully do if you can get in here. Maybe you could perhaps write some code to squirt thermal image data out the UART port. Perhaps, maybe even, I don't know if there's a direct connection to USB, maybe even run it on a P. If there's a USB connection to the processor, you could perhaps get it to run as a USB device on a PC or something. But it's not something I'm hugely interested in pursuing. Right, I've soldered a couple of wires onto the I2C and SPI buses because those are the ones that we want to look at. One useful thing I did find is that this will actually run when it's not plugged into the iPhone. If it's not plugged in, you turn the power button on, it will turn on for a few seconds then power down again. But if you actually put it on charge, it will actually stay on indefinitely, but it will still run the sensor and get all the data out. So that's one less thing that you have to have plugged into the setup. So it looks like we probably can get the socket at some point in the future, but that's no good to us now. Fortunately, there's actually another version of this socket, which is a 24-pin one, which actually has the same dimensions. It just omits the end pin on each row, and these are actually available ex-stock from RS. So I got a load of those in. Using this as a basis to start with, we can actually make the 32-pin version. First thing I stripped the metal casing off of it just because that got in the way. Made a little breakup board with the full 32-pin footprint, put some solder paste on, and then just reflowed the 24-pin socket onto that footprint. I then gently lifted off the plastic, which then leaves all the 24 contacts in place. And then to add the other contacts, I basically cut the side off another one of these sockets to give a sort of jig, pulled a contact out, and then just placed one contact into the end of this jig, then slid that over the contacts that were already soldered and then flowed that pin down. So by repeating that process 8 times, we now have the full 32-pin array of contacts. Now obviously these are rather fragile because the only thing holding them on is the fairly small solder pad. So what I did, I machined a little square frame out of 3.2mm PCB material. These support the back edge of the contact so that when the spring pressure is applied, it doesn't put any force on the PCB joint. And when the frame was on, I then also just put a little bit of super glue on the back edge of this to try and limit any lateral motion of the pin, which again might put some stress on it. So hopefully that'll make a not a super robust contact, but enough to actually get the thing working. Right, so it's actually been fairly straightforward to get data out of this. In fact, I'm not actually using the I2C interface at all. This is literally just the data as it comes without any configuration. In fact, I've only had a fairly brief play, but I can't actually get the I2C to have any obvious effect on the output, but it could just be that you have to send the commands sort of between reset and starting to pull the data out. But basically what we've got is we've got the raw 14-bit thermal image data coming out. I've just got some very crude min-max algorithm to scale the displayed image to the min-max of the incoming data. So for example, if I wave a hot soldering line in front, everything else sort of disappears out because the max is a lot higher. Yeah, it seems to work pretty nicely. The setup is really simple. We've got the Lepton module, we've got 2 voltage regulators, we've got a 2.8 volts which is running the processor and the supply for this and the I/O voltage. We've got a 1.2 volt, that's a switching regulator because that's pulling about 80 milliamps. going from like 3.6 to 1.2, it's worth putting a switcher in there just to get the improved efficiency. But for the 2.8, the gains are fairly minimal, and the current draw on that, actually the module current draw is about 15 milliamps. There's probably about another 30 milliamps or so for the rest of this stuff. But from a 3.6 supply, it's probably marginal. It's even worth putting a switcher in there. So apart from that, we've got 25 megahertz oscillator here that you probably can't really see very well. It's just a little 2.5 by 2 millimeter surface mount oscillator module, and PIC32. And a PIC32, this is output in composite video. The way this works is the PIC32 has got is basically generating the composite via a DMA task. So we're using pulse width modulation to generate line sync. On each line sync pulse, we're setting up the DMA to output a line of data out to port B, controlled by a timer interrupt running at the pixel clock rate. And this works quite nicely actually. Obviously we're generating quite low res video, we're only generating 80 pixels across. There's a small amount of jitter due to the interrupt latency, but it's for this low res application it works quite nicely. It's literally just the output's going to a symbol to our resistor network and another resistor to mix in the line sync. The nice thing about composite is you can then feed it into all sorts of other things like monitors, little DVRs and so on. The disadvantage is it's quite tricky to get colour because you need to do PAL encoding, and there don't seem to be any low-cost digital input PAL encoder chips. There's quite a few analog ones, but it gets a lot more complicated. So, but for just vision applications, monochrome is probably fine. But it means that, for example, if you wanted to produce a composite stream for sticking on a quadcopter or something, in principle all you have is the module, a little PIC and a QFN package, some resistors, 2 voltage regulators, and that's pretty much it. And power draw on that is going to be about 90 milliamps at 3.6 volts. So you've potentially got a very nice little low cost, very small, very low weight thermal imaging system. On a remote control or quadcopter thing, you might want a narrow field of view, so you might want to maybe look at using a different lens, depending on the sort of range of things that you're looking at. But that seems to work quite nicely. Now, there's only one issue at the moment. There's only one issue I've got at the moment. Basically, what you do is you just read a fixed number of bytes over SPI, as we saw in some of the scope traces earlier on, and you either get a line of image data or you get like a status packet. And under some circumstances, it does actually get out of sync, and you sort of start getting sort of packets, garbled packets. That seems to be a function of the time between when you reset and when you start reading packets out. And I think there's probably an I2C command to help with that synchronization, because I've got it working quite reliably by just leaving a fixed delay between resetting and pulling the first packet. But it seems to be quite sensitive to getting that right. So there probably is a way using the I2C to either get in sync with it or to force synchronization. But I mean, it's usable as is at the moment. But also, if it does go out of sync, you can actually detect that, because the non-image packets have got that fixed data pattern. You can actually use that so that if you're not seeing that pattern, you can just delay it for a while and then you can get back in sync within about a second or so. Apart from that sync issue, I don't think it's a huge reason to delve too deeply into the I2C stuff. Although, say, the module in principle can produce various different data formats. And the 14-bit data is actually quite usable as is. It doesn't take a great deal to format to get all the sort of stuff you like. You normally want out of a thermal imager. Although in principle it can do the RGB and the AGC internally. It seems to be quite usable as is. Now it does look like although this is sort of fairly low level 14-bit data, it does look like it does include the non-uniform correction, it's automatic flat field correction in there. So if we turn this on, we do see a bit of these lines and this fixed pattern noise, but that does fade out fairly quickly to give a fairly clean sort of flat image. So if I power this up with just a piece of paper in front of the lens, so it's got a fairly flat thermal image, initially we do see quite a few sort of lines and so on, but they do fade out fairly quickly. There's still a few pixels, sort of slightly hot and cold, but a lot of the night, your average image, you don't really notice any major amounts of noise on it. One thing I noticed which was interesting was that you appear to get a frame out of this thing 25 times a second. We know that that's fairly unlikely, if only because of the export control thing. So I've actually just done a short recording and then single stepped it. I've also added, there's a little dot that moves across one position every received frame, and if we actually single step this, we'll see that every third frame we get a change. There's some fade in and fade out, which I think is due to the fact what I did was video that monitor as a quick and dirty way of doing this. But you quite clearly see that it's sort of every three frames of this we get one output frame, and that corresponds to 8.6 frames a second. So it looks like it's just copying the frames, or giving us the same frame 3 times. Although say I wouldn't be surprised if there was some version of this at some point that can actually do high frame rates, but that will be subject to export control until they get rid of that rather silly limitation. I will put up a web page with all the information and resources on all the protocol that I found out, and I'll probably stick some code up for this at some point. Check that back regularly, just if you are seriously interested in looking at this thing. So all in all, this is a very nice little module, pretty easy to drive. The resolution is low enough, that it is capable of being driven via microcontroller if you've got somewhere to sort of throw the data that you're gathering. I do have a couple of projects in mind. I'm going to be playing around with this, which no doubt you'll see fairly soon. I think what will be really good though, what Flir should really do is make this readily available, because I'm sure there's all sorts of applications that people will come up with that they've never really thought of. So if they really want to be clever, they should get this into DigiKey or Mouse or SparkFun or somewhere so that people can actually just buy them. You can, if you don't mind sort of spending $350 on a Flir One, you can buy one of those and rip the center out quite easily. It is socketed, so you could put it back in again afterwards, so it's not too terminal. And with the various upcoming potential competition from the Hemmer Imager and Seek Thermal, they could have quite a lot of competition, so I think we could well see the price of this drop. This module, I did actually make an inquiry fairly early on, and they said that basically if you want to buy these modules, it's a minimum order quantity of 1,000 at $250 each. But obviously, these things don't cost anywhere near that to make, but they've got a huge amount of investment to recoup. But I think as and when we see some competition, I think we could see this module price dropping quite substantially. So I think there could be all sorts of really interesting applications coming up with it. So we'll wait and see. But I've got a couple of projects that you'll see fairly soon, at least one of them anyway. And I will be documenting it. So if you're interested in doing this, check out that web page and get in touch. Right, so let's start by taking a look at the I2C. Now you can see we've got it's sort of semi-regular intervals, but there's quite a lot of jitters, no sort of really obvious pattern, but it seems to be doing stuff on a sort of quite a regular basis, a couple of times a second or so. And there seems to be quite a few different things going on. So obviously the first thing we do is we turn on our I2C decode. And we can see looks like we've got 2 different addresses. We've got 2A and we've got 4F. These are the 7-bit addresses, excluding the read-write bit incidentally, mainly because the I2C trigger only supports that address mode, so it just makes it consistent. So it looks like we've probably got 2 devices here. One will be the sensor itself, and the other one I'm guessing is probably going to be that temperature sensor that we saw on the front shutter. Quickest way to make sense of this, we can set up an I2C trigger, and we make it trigger on a specific address. So we could trigger on just the 2A address there, and there seems to be quite a lot of stuff going on still at 2A, so let's take a look at that 4F address. So we're now just triggering on the 4F packet, so we've still got those 2A's in there, but we're always triggering on a 4A at the 4F. Now it's doing a write and then followed by some readbacks. The timing's sort of a bit jittery, so it's a bit hard to make sense of, but one nice thing that the scope's got on the decode is it's got a list mode. So this actually takes all this data here and it actually gives you a tabulated list. So now we can actually see that it looks like it's sort of reading a sort of 2-byte value. I think the reason this is truncated is just the time base, it's just falling off the edge. If we slow the time base down here, we can actually see things. So from 4F we're reading this value which is changing, so I'm guessing that's the temperature. So we confirm that if I just put my finger on the sensor. We can see now that value is now going up. If I give it a quick scroll to freezer, it's now going down, so that's definitely the temperature sensor. So that's something we don't really care about, so we can just ignore that. We've just changed the triggering on the that 2A address, which is clearly the sensor address. Now again, we've got quite a lot of stuff going. What's a bit annoying is because these are going over different time spans, it's not ideal from the point of view of trying to capture everything. One of the problems on a lot of scopes is you just take that trace, you capture all this data. The problem is that you zoom in, you don't have enough memory to actually resolve it all. This is where segmented memory comes in very handy. I've talked about this on some of the other reverse engineering videos. With segmented memory, what happens is instead of filling the whole scope memory on a single trigger, you tell it to break the memory into a certain number of segments, and on each trigger it writes to one of those segments. So if we set our time base to look at this sort of time scale, we then turn segmented memory on, tell it, say, I don't know, 100 segments. Now when I do a run, it will trigger 132 times, and then we can step through all those packets separately. So if I just do a run now, it will just sit there. It's sort of telling us how many segments it's acquired. Let's just stop it now. It's just running through them. So now what I can do, I can actually step through each individual trigger. And one of the problems, particularly with I2C, because packets are of varying lengths, you don't necessarily get one packet or one set of packets per acquisition. So what happens, for example, here we're actually losing the end of this one. But obviously, if we set the acquisition too slow, firstly we waste memory, but also we might get like one packet here and then just one starting here and lose the end. So you need to do a bit of messing around to get a sort of general good overview of what's happening. But let's just take a look at this. Again, if we stick the list mode back on, again we can step through the segments, and this is sort of stepping through our acquisition, and it's also time stamping it from acquisition to acquisition. That's the other useful thing. So although it's taking sort of several triggers, you actually know what the timing is. So if we look through here, most of these seem to be sort of, we've got, for example, the writes tend to be 0, 0, then a value, and then either some additional values here or a read. The other ones, for example, so we seem to have sort of a few different types of action. We've got, always seems to start writing a 0. We're also catching a bit of temperature sensing data here in the pre-trigger. So yeah, this will still contain some of that temperature information. We've not filtered it out. All we've done is we're triggering on the 2A stuff. So that's what we're going to start seeing. So it looks like we've got a few different commands. We've got 0, 0, and then, right, so if we just have a general browse around and look at what commands we've got going on, they all seem to be 0, 0, and then 2, there's a 2 and a 6 and a 4, and there's also an 8. Those are the only ones I've seen, so those are probably reading and writing registers within the chip. I was actually expecting to see quite a lot more, being used to things like cell phone cameras that just have crap loads of initialization data. There also didn't really seem to be anything specific happening at power up, so there didn't seem to be a lot in the way of initialization data. So we've got, for example, the 06 and 04 seem to be writing values, whereas the 02 is reading, so that's reading back that 06 value. And then there's this 08 which is reading back a 2-byte value. So let's just, what we can do is we can actually do a more detailed trigger, because obviously we can see this stuff in the listing, and we could in principle save all this out as a CSV file and go through it, but it's a lot quicker just to do it real time. So what we can do is now, instead of just triggering on that 2A, we can actually extend the trigger to trigger on more specific parts of the I2C packet. So we can, for example, make it always trigger on this 08. So although we'll get all the other stuff, this value will be the first in the list, so we can scroll through and look at different readings and look at it in real time. So let's just set that trigger up. I'll just turn segmented off so we get the real-time display. The other thing that's quite handy, you can sort of play around with the trigger and see if it's not triggering there, we're not seeing any of that value. So for example 0, 0, 0, 0, we're not seeing any triggers, so we're not, those packets aren't happening. But for example, if we change that to 02, we now see the triggers on that 02 value. So although it's a little bit of a fiddle, you can actually step through to almost figure out which ones are there without having to look through the list. It at least gives you a fairly good idea of what's there. So if we set this up to the 08, and again if we go into lister mode, also we can play around with the trigger point just to filter out stuff that we're not interested in. So if we move that back to there, we're now actually seeing just the result of that 0008. And that, I noticed earlier on, that was actually sort of changing slowly, so I suspect that's reading a die temperature on the sensor. So if we just give this a little touch of freezer, we can now see that value dropping. That's dropping now quite quickly. So that's clearly a temperature sensor. My finger on it, warm it up again. Again, that's timing. So of those sort of 4 commands, we've figured out what at least one of them is. So the other ones, there don't really seem to be that many of them, so in terms of figuring out what they do, I think maybe it's just a case of, once we get this running out of the unit, just throw some commands at it and just see what happens. I suspect there's probably some configurations. For example, the datasheet says that it supports different output modes, RGB and 14-bit and so on. So I suspect there'll be sort of some mode bits that we'll just have to do a trial and error just to see what happens, and we may find that there's ones that control the various output formats, these other ones. So this O2 readback, I did notice when I was, this O2, most of the time it reads back 06, but sometimes it reads 07, so I wonder if that's maybe polling for a new frame available. Again, because the timing is a bit ragged, it's a little bit difficult to get a good handle on what the actual time intervals are. And because that's a readback, the trigger on this isn't quite clever enough to actually be able to trigger down on that read value. If we could trigger on the 07, we can maybe look at how often that occurred. And so the other ones just seem to be writing fairly small and generally not very changing values. Yeah, so these 04, it seems to be doing 04, 02, 14 and not really anything else. Yeah, again, the 06 seems to be pretty much doing 0001 most of the time. Now I did see one of these change when I did a calibration. I'm trying to remember which one it is. Let me try and catch that. I've been playing around with this before starting this video, obviously, just to get a feel for what's going on, but I'm just now just stepping through the various things that I looked at just as in an abbreviated form. Yeah, so this 04, if I do a calibration, we see that changing, so there's something being written to the device during the calibration process. I think that's about the only one I've seen changing though, so we've fortunately, we haven't got like a massive torrent of all sorts of different commands to figure out, so hopefully it shouldn't take too much effort to work that out. So I think that's probably as much as we need to look at the IC2 for the moment. What I will do is I'll just save a load of this so I can go through it, because obviously I don't want to be moving that sensor between sockets all the time, so I want to just archive a whole load of these dumps so I can just trace through it to, for example, just to look at all the different variants that get sent to it, just for reference if I have any trouble getting the thing running. Right, let's take a look at this SPI bus data. As we saw when we had a quick initial poke around, we've got a chip select, SPI clock and a burst of data. Again, the timing seems to be pretty sort of random. There's no, it's sort of vaguely bursty, but there's also, I think the fact this thing's running Linux may well explain the lack of sort of solid timing going on here. And again, if we look, it looks like we've got a mixture of sort of short packets and sort of fairly long packets going on. And once again, the protocol decoder on the scope is going to help us figure out and just save a lot of time. Obviously, these are all things you could decode, with external hardware or dedicated protocol decoders, but just having it on a scope just make it so quick, because you get an instant picture of, the relative timing, the signal levels, and some decoding very, very quickly. So this can just save huge amounts of time and effort. So if we go into our serial decode, SPI mode, right, so now we can just grab packets and it gives us the first few bytes of it. One thing that's really handy, it tells us how many clocks are in that burst, so that will give us an idea of what the data means. One thing I find a bit annoying though on this scope is it seems to actually be using the display data rather than the acquisition data, because if you reduce this, it actually starts lying to you about the number of clocks, because it's looking at how many transitions it can see in the current display, which I think that's really bad. It should just say, I don't know, or give you some question mark thing. I mean, to actually lie about it is really, really confusing. That's just something that, I don't know, it may be specific to this scope, I'm not really sure, but it's just something you need to watch out for. Now, 1312, let's see if we can make sense of that. We know it's, our data's coming in 8-bit bursts. So let's see how many bytes that is. 1312 divided by 8, 164 bytes. So that makes a lot of sense. If we know the sensor's 80 pixels across, we assume it's sending 2 bytes per pixel. It's it's one line plus 4 extra bytes. And if we look at these, we've got these 2 different types of data, and it looks like we've got the short ones that have just got a bunch of FFs, or the longer ones that have got which is probably the actual video data, and again we can use the lister to actually see a bit more of this. Unfortunately, because these are fairly fast, we can't get too many acquisitions, we just run out of memory fairly quickly. And again we can use a trigger so that we can actually trigger on these two packet types. So if we go into SPI trigger, we can say let's trigger on 8 bits. What we're seeing, so we're either seeing a 0 or let's just trigger on an all 0, see what that looks like. Right, so now we're only seeing the 0 packets at the start. So now we're only seeing the 0 packets. And one thing I noticed fairly quickly is there seems to be some sequence going on. We've got 0, 1, 0, 2. And so again we should be able to get some information if we do a segmented acquisition and then look at the lister. We can probably make a bit more sense out of this. Yes, if we, as we step through the segments, we can immediately see this value is incrementing. So that's probably something like a line number, so it's starting at 1. And then it's stopping at 3E, which is 62. So again, that's almost certainly a line number. And again, if we sort of look at the lister data, we can actually see that more clearly. So if we go, so we can see that's literally going 1, 2, 3, 4, 5, 6, 7 on those packets. So that's obviously a line number. The next bytes look fairly random. I'm guessing that might be a CRC or a checksum or something, but if we look further on we're starting to see a very clear pattern, and we've got a low value, a high value, so I'm guessing these are probably the pixel values, and knowing other Flir stuff, it's, yeah, we saw a reference to 14-bit in the datasheet, so my guess is that's a 14-bit pixel intensity value. Right, I was trying to look at some changes by waving my hand over it. It turns out this camera is actually pointing straight on my light. That looks like it's almost exactly at body temperature. But if we look at these high bytes, these ODs, if I just sprayed a bit of freezer onto a bit of plastic, I'll stick that in front of the camera. You can see these change immediately. So this is clearly heat data. So that's a cold surface it's seeing now. It's gone down to 0A. If I take it away, it's gone up to OD. If I wave a soldering iron in front of it, that's now shot up. That's actually gone up right up to 3F, so that's obviously just saturating. So I mean that looks fairly straightforward. Let's take a look at that other data. So I mean, yeah, these are clearly we've got 60 odd lines of 80 14-bit words per line, so that's clearly the thermal data. I mean, for something like the iPhone thing, I'm sure it would just be using the 14-bit data and doing all the colorizing in the iPhone app. There's no reason for it to be doing that on the module, although the module looks like it can do all the palette stuff and auto gain control by itself. It looks like this is just taking the raw 14-bit data and dealing with that by itself, which makes sense. You know, it's got plenty of processing power on that ARM chip, and it's got plenty of processing power on the iPhone, so there's no it gives you the maximum flexibility for having different palettes and so on. Right, these other data packets, there doesn't seem to be a lot here. It looks like there's a fairly fixed header pattern, but there's also some data here that's changing. Now we've got here, and that's clearly a count, so we've got a value here that's incrementing, so that's probably just a frame count. So that might just be a frame sequence, so you can check that there's data's not going missing. And there's some other data here that seems to be sort of changing in a slightly less obvious way. I mean, this might be feeding back stuff like the spot temperature measurement, that sort of thing. So it's probably a little bit difficult to figure out what a lot of this is. But there's not a huge amount of it. Well, these used to be bouncing around a little bit. I suspect that first byte that we saw may well be some sort of... If we go back to the beginning, I'm just triggering at the moment on anything starting with F, but if you can see we've actually got a few different versions, so I wonder if each of these indicates a different type of data. So if we actually trigger on a more specific type, so we've got 0s, 2s, 3s, 1s, 4s, 7s. So we should be able to see what we've got again by using the trigger. If we now trigger on 8 bits, Unfortunately this isn't quite as nice as the I2C. You actually have to set them a bit at a time. You can't just tell it to look for a byte value, which is gets a little bit fiddly. It seems to be sort of fairly sporadic what it's displaying, which is odd. There may be could be there's another field in there that gives some indication of what this data means. I suppose it's also possible it may be related to the I2C data, and the I2C data is a request and then the response comes back through here. Of course the problem is we can't simultaneously decode I2C and SPI on this thing. Well, this top line is the I2C, so I mean, it does look like it's never doing the same thing at once, so it may well be that it's doing an I2C request and then reading back the data from it. Again, I think this might be easier to just hook up to my own system, just throw those I2C commands and then just see what happens when we try reading back the SPI data. If we look at the bigger picture, it looks like we are getting, a load of these little ones and then the main burst of frame data every time. That seems to be fairly consistent. But there doesn't seem to be any real consistent relationship between this stuff and what's going on the I2C. Some of the I2C seems to actually be interrupting it sometimes. So I don't think we've really got anything happening in terms of sending an I2C and then getting some immediate response. There's definitely some sort of small bits of information, then the main bit of video here. So maybe that's things like some spot temperatures or something, but we need to analyse that a bit further, but I don't think that's going to be particularly necessary for actually getting some images out of this. Incidentally, the SPI data in is always 0. I even shorted it to ground and ran it and it didn't seem to object to that, so it's not doing anything at all with the SPI in. Right, there's something interesting happening with these pins. These are the pins which I believe are the reset and the power down pins. And that's not confirmed, they might not be, they might be GPIO pins, but certainly pulling them, either one of them low, makes the thing sort of fall over and stop working. So on initial power, I'm just hitting the reset button on this. You get what looks like a fairly plausible thing as it starts up. It's resetting, it's taking out reset and running, and here's our I2C starting up. So I mean that's pretty much what you'd expect. Okay, maybe can't tell which is reset and which is power down, but it doesn't really matter. But there's something else going on. And this happens almost instantaneously after reset, so it must be way before anything boots. Two things that seem to be happening. First thing is this very, very fast burst of data. Now the fact that this is happening, this must be coming from the processor, not from the module. Firstly, it seems to be at 24 megahertz, but also the fact that I'm pressing the reset button, not powering it up, so the module in principle doesn't actually know what I'm doing. I'll see if the other I/O pins are doing anything at the same time. But so the first thing we have is that. Then the second thing is this. It seems to be actually clocking some data in. Now whether that's something to do with the module, or that maybe even that's something that what's odd is that that is literally almost instantaneously from reset. So I almost wonder if that's actually a sort of something that the processor's bootloader is doing, and it just happens to be using those pins. So maybe something the pins are doing before they're being initialized to act as those functions. Maybe some bootloader function in the chip. But so I wonder if that's actually something that's really needed or just something incidental. That's curious. That needs looking at a bit further, I think. Yeah, I think I confirmed that. There was the track on one of these pins went round sort of via to the processor and then onto this resistor. So because I could get to both ends easily, I just cut that track and join the two pins together, because if they're sort of power down and reset, it's probably not going to matter too much if they both get asserted at the same time, and that just works and that's working fine like that. So I think those waveforms may be some sort of artifact of a shared function pin that's used by the chip's bootloader, so hopefully you don't need to do anything with those to get it to run. And just to make doubly sure, I've actually now cut both those tracks to those pins and just tied them both up to the IO VCC supply, and that just starts up and runs. And that, as you can see, that just starts up and runs just fine. So I still don't know which of those is reset and which is power down, but I don't really care, it doesn't really matter. The power down function on this pin, on this chip, is, it's not going to be that useful because you're going to be running these things from regulators that have probably got enabled pins anyway, so that would probably be a better way of powering it down than using its own power down anyway. So tying those together. Obviously it probably does make sense to have an active reset thing, but I've literally just pulled those straight up and it's working, so I'm not at all concerned about what those pins are. Right, there's one final thing I wanted to check before I yank this thing out of the socket and start prodding it with my own hardware, and that's to see if there's any evidence of any sequencing of the power supply rails. And this thing's got 3 different supplies, and you sometimes find that devices are fussy about which order those supplies actually come up in. I've connected 3 scope traces to the 3 supplies, the 1.2, the 2.8 and the 3.1 IO, so we'll power it up and see if there's any obvious sequencing going on. And I think that'll be a no. I mean, this is 500 microseconds per div, and these are clearly just the natural rise times of the regulators. There's no obvious signs of any sequencing there, which again hopefully makes life simple. So hopefully we've now got almost everything we need to start sort of poking at this and trying to get some life out of it outside of its iPhone.